Hey, so welcome back, everyone. Hey, I know everyone's excited about their projects and their proposals. Hopefully, you turn those in. Yeah. So, is there something going on up there you want to share? What? All right. Question.
Was it one per group?
Yeah. So you just turn one per group. We're going to try and figure out how, after we know what the groups are, how to say that, it's defined that there's a group and there's one turn-in per group. But we didn't know the groups yet. So if you just turn in one per group, that's fine. If you turned in multiple per group, it's also fine. So there are a few questions about the project proposals that I'll try and just say again now. So the first thing, so some people said they turned something in, but now, already they're thinking of changing what they want to do. So that's fine. So if you want to change it, that's fine. When you get to the next stage, the data collection report, which will be due in, let's see, the next thing, the data collection report, is going to be due on February 23rd. So when you do that, just make sure that at that point you kind of just have a preface saying what the new project is, so we understand the context. The other thing, is there a question in the back there? Sir, you have a question?
No, I have a question.
Okay. Yep. Question.
When can we get feedback?
Well, it's not going to be right now. We need to read through them. We'll try and get through these in the next week or so. We'll try and do this as soon as possible. But I can't give you all feedback right now. If you're really eager about that feedback, please see me during my office hours, or you can send me email offline as well, and I'll try and respond to it. A lot of you have come and talked to me already, and I've kind of implicitly given you approval about stuff. Again, remember, my office hours are right before class for like half an hour, 45 minutes. I'm in here, and then Thursdays at 11 to noon. So the other thing with the proposals that has come up is, a lot of people seem to want to build like a classifier as kind of, it seems like a natural thing to do, and it is a very natural thing. It's what the entire machine learning class is about. What's in the project write-up is not that you can't use classifiers, but that the central part of the project can't be just building a classifier. So a classifier is when the input is some data, say X, and some labels, and usually these are -1 and +1, or they could be something else. And so you think of this as XL, and so every data point has a label associated with it, and then the goal is some sort of function that takes in your data and passes out some classifier. Or it doesn't necessarily be the data. Maybe this data lies in some space, and so then this is from the space that the data lies in. So basically, the idea is if you get a new data point, you want to predict what the classifier is. So whether this is going to be, I'm predicting that this person is going to I'm predicting whether the Patriots are going to win the Super Bowl or the Seahawks are going to win the Super Bowl based on the data from the whole season up until that point, right? So that would be building this function, right? So you can't just do something that's building this, but there's a lot of work in how to describe this value X and these L's, how to build this input data, and how to pre-process it before you do this function. And then there are lots of black box functions, way to build these classifiers you can use in the project, but the focus should not be constructing some algorithm which works for this function f. Okay? Yeah.
So if we only have the data set x, we try to also do something like classify, but the L is not given. We are going to.
Yeah, if the L is not given, then this is usually what's called, then if there's no L, then this is equal to unsupervised learning. And so examples of this will be like clustering and maybe doing like regression. Or it may not. Yeah, yeah, right. So this is fine. So doing when you don't have L is fine. When your goal, when you have X, or when your input is actually some other set Y, and you create some set X, which works well in the classifier. How do you create X from Y? These are other sorts. These are steps within the pipeline, and exploring those steps using techniques from class will be interesting. Okay. Okay, so now and also the next homework, which will be due on February 18th, so that's a week from Wednesday, is not posted yet, but we'll probably post it tomorrow. It's basically ready, but we're just tweaking the day sets just a little bit that you'll operate on. So look for that. If you're eager to get started on that, it'll be out soon. Great. All right, so the topic of class today is going to be distances. And so there's some part from locality sensitive hashing that we didn't finish, and those I'll I'll interject that after we talk a little bit more about these LP distances, how to apply LSH on those. There's kind of one of the unwritten things about how you might often be presented some task in data mining is often you're given as input some data, and then your goal might be something like clustering or outlier detection, or some form of regression. Okay, and so you're given a data and you want to do these tasks, but typically what these tasks need, so these tasks take as their input some data plus some distance defined on the data, right? So some distance is some function d, which takes, so your data is from some space x. So we'll go through some examples. These could be sets or vectors or something like that, or it could be something less clean like documents. And you define some distance, which will, so it's a bivariate function between two elements of this space, and it gives you a value, right? And this value is usually between 0 and infinity, right? We talked about this earlier, right? So it's some function which goes between two distances and tells you how far apart things are, right? The smaller the distance, the more similar the objects are. And so this is needed for a lot of these different tasks, but you're often just given the data. The distance is something you have to choose, right? So you have to choose, okay? And so the point of this lecture is that you actually have a lot of choices, and unfortunately the answer to what is the right distance is not always so clear, and there's not always a right answer. Instead, I'll try and give you some insights of how to choose a good distance and what you should look for, and kind of give you an idea of the space of different distances you could choose, how general this kind of notion is. And so there are kind of two ways of kind of deciding whether a distance is good, right? The first way, how does it model the data. Okay, and this way is kind of is necessarily, anytime you kind of do modeling, it's going to be somewhat ad hoc. It's going to be somewhat, based on looking at how it works. You're going to take two things that you know are close based on your underlying knowledge of the domain, and look at the distance and see if it gives you a small value, and look at two things which you know are completely different and make sure it gives you a large value. Make sure this makes sense just by looking at it and thinking about different scenarios. And the other part is going to be based on the mathematical properties. Okay, and so the most central one of these is if the distance is a metric. So the distance does not need to be a metric to be a good distance, but this is often a very nice property to have for various reasons that we'll talk about. And there are other important mathematical properties that help you tell whether it's modeling the data correctly. Okay, and so we defined a metric before, but let me redefine a metric. A distance d that's going between two sets 0, infinity is a metric if and only if it satisfies these four properties. Okay. So the first one is that the distance, must always be greater or equal than 0. Well, this I specified, up here already. So M2 is that the distance between two objects A and B equals 0 if and only if A is equal to B. So they're only equal to 0 if A and B are exactly the same thing. Right? And we talked about this before with the sets. The Jacquard distance is one of these examples of a metric where you have a distance, which was the Jacquard distance between two sets A and B, which was equal to 1 minus the Jacquard similarity between A and B. Right? So this was a metric, and between two sets A and B, this was true. They were only 0 if the sets were the same. But if we model documents as sets, then if this was a distance between the documents, it might not be a metric, because two documents which are different could map into the same sets. So M3 is that has the symmetry property that D of AB is equal to the distance between B and A. So this kind of seems like a natural thing, but not all useful distances have this property. And the fourth one is the triangle inequality, is that distance between A and B is going to be less than or equal to distance between A and C plus the distance between C and B. Right? So this you can kind of see if you have A and B and C, then if going from A to B is measured by this blue line, it should be cheaper than having to go through C. It could be the same if C happens to lie on this path, right? So this is why it's called the triangle inequality, because this part of the triangle is less than the sum of these two parts. Right, so this seems like a natural thing, but again, not all useful distances have this property. Okay, so one thing is that this Jacquard distance is a metric, and if we make really good progress, I might go through in detail why this is a metric, but there are just kind of discussions of this in the notes more carefully. The first thing, so what I'm going to go through now is, so a couple more things. If something satisfies M1, M2, and M4, then, but this is, sorry, let's see, M1, M3, and M4, but not M2, then this is called a pseudometric. Okay, so it doesn't have this things where they're equal to 0. And so this kind of was like the thing with the distance between documents mapped to the Jacquard distance. We'll talk about another interesting way where you have another distance that is a pseudometric, which is very useful. And then if something satisfies M1, M2, and M4, but not M3, then this is what's called a quasi-metric. And you know, both pseudo and quasi mean kind of like it's not quite, right? And I'm not sure why pseudo is omitting M2 and quasi is omitting M3, but they're properties that are almost like these metrics, so they have a lot of the nice properties, but not quite all of them. So this would be that it doesn't satisfy this property of symmetry. And we'll talk about a distance that does not satisfy the symmetry property that's really useful. It happens also not to satisfy the triangle inequality, so it's not a quasi-metric. But I'll give you an example of how you can see one of these that is still worth using, even though it doesn't satisfy all these properties. Okay. All right, so the first set of metrics that we're going to talk about is a pretty broad class that are called the LP distances. Okay, and so, and the most famous of these is the L2, which is the Euclidean distance, but let me define this more formally first. So we'll say dp, and so this will be defined between vectors in RD, so in d-dimensional Euclidean space. Or I guess this usually kind of implies you're using the L2 distance, but this is going to be a distance between these d-dimensional vectors where every element is one of the reals. Okay, so so now assume A and B are these vectors. So remember a vector. So A is going to be equal to A1, A2, up to AD. Okay, so there are these D things which are ordered. So D is typically used as dimension and also as the distance. I'll always use a subscript on the distance. Hope that's not too confusing. Okay, so this is often also written as A minus B with a P subscript here as this norm of the difference between these two. Okay, and this is an important property. It means that it means that these vectors are going to be what's called shift invariant, which means that if you add to every coordinate or to even just one of the coordinates some value to both A and B, it's not going to change the distance because that part's going to get subtracted out. So you can write it as the difference of the two values. And then formally, what you do is you sum over all of the coordinates. You take this to the power p, and then you take the pth root. So it's written 1 over p. So you take each element to the pth power, and then you take the whole sum to the power 1 over p. Right. So the most common form of this is the L2 distance, which is A minus B2. And often if I don't write this subscript 2 here, it's referring to this L2 distance. The 2 is kind of the default one. And then just to see this more concretely, this is I equals 1 to the d of ai minus bi squared, and then this to the power 1/2 is a square root, right? So this is a square root, and so if you draw these points, so I can draw them in 2D, and we'll talk about these over this in the next lecture, what happens in higher dimensions a little bit. So say this was the x coordinate and the y coordinate, and so it's a vector of length 2. This is x, and this one is y. Then if I have a point A and another point B, then it's just the length of this line, straight line between them. Right, so this is the L2 distance. So another common one is the L1 distance. And this one, this 1 over p, this p is now 1, so this whole thing drops. Right? So this is now just the sum and instead of power 1, actually, this should be the absolute value to the power p. So it's ai minus bi, absolute value. So it's the sum of the difference of the coordinates. So now if I look at this one, kind of, you can think of laying down this grid here. And I know you can't see the green all that well. Well, you can see it okay. You can see it almost better than I can on my screen. And what this works like is you can think of walking on this grid, and now your distance between A and B is forced to walk on these grid cells. So you can only, you go the x distance and then the y distance. So this is sometimes called the Manhattan distance. And that's because, you know, it's like how many, so like you could also, you know, if you're on the East Coast, you might call it that, but in Salt Lake, you might call this the Salt Lake's, you know, distance too, because the streets form this nice grid structure, right? So if I'm getting from, so like if I'm going from Sugar House to downtown, I can't go like as a bird would fly. The bird would fly maybe as the Euclidean distance. It would just get up and fly over all the buildings, but a car would have to go on the streets, right? So even if you were a bike, right, and you said, I'm going to zigzag, and I'm not just going to go in this way, I'm going to kind of zigzag back and forth to get from A to B, the distance will be the same. It doesn't matter if I do all the x coordinate and then all the y coordinate, or if I alternate between them, I'm still the sum of these is going to be the same, right? So if you're forced to walk along the axes like this, then it doesn't matter which way you go. So let's call this, let's fix this, the SLC distance. All right. Okay, so one of the cool things about these, let's see if I can move this camera. Okay, so is that there's a cool way of visualizing these distances. And so I'll just do it in 2D, but we'll talk about it as it gets to higher dimensions. So it's x and y axes. And so we'll say that we're looking at distance between A and B. We'll say that A is going to be here at the origin. So A is going to be equal to the all zeros vector. And then we'll look at the distance to any point B. In fact, what we'll look at is a ball of, we'll look at a ball of distance 1 under these different metrics, right? So I can go out and I can say this point is coordinates 1, 0. This point is coordinates 0, 1. This point is -1, 0. And this point down here is going to be 0, -1. Okay? And so, if in both of these metrics and some other ones we'll talk about, these points on the axes are always going to be exactly a distance 1 away. So they're all going to be on the boundary of the unit ball of distance 1, but how they go in between this area is going to differ. Right? So we'll start by drawing the unit ball for Euclidean distance, and it's going to look just like a ball. Let's see how well I can draw this here. All right. There's actually some... Oh, okay, let's go back. So there's actually some utility for drawing shapes, but I'm afraid to use that. Well, maybe I shouldn't have been so afraid. But okay, so let's just look at this upper quadrant here. It should look like this. It's symmetric in all quadrants, but this one I drew pretty reasonably. So, okay, you guys are laughing at me. I'm gonna do some surgery until I get this right. So, these parts aren't so bad. It's just this one. It's not that bad. All right. All right. Okay. So here we go. And this one goes out a little bit too far. All right. Okay. So it should look like this nice circle. All right. So you're going to get this nice actual circle here, right? And this corresponds with the L2 distance, right? Any point that is on the circle is exactly a distance 1 away from the origin, from point A here. So if point B lies on the blue circle, its L2 distance, D2 here, is going to be equal to 1. All right, so what if we try to draw the same circle for the L1 distance? Right? I'm telling you, it's going to include these points on the axes. But is a point here, what is the value of the L1 distance, a point right out here? Is that going to be, and let's say this point is, I think this value is 1 over square root 2, 1 over square root 2, right? So if I mark a point here, this will be 1 over square root 2, 1 over square root 2, right? So if I were to look at this point and measure the distance from 0 under the L1 distance, is this going to be greater or less than 1? Okay, let's vote. Who thinks it's going to be less than 1? Who think it'll be greater than 1? And who didn't vote? Okay. And who still hasn't voted? Okay. All right. Well, we're slowly approaching everyone. All right. So it turns out this is going to be, well, let's just write this down. So what's 1 over square root 2? It's going to be, it's like 0.7, right? So it's going to be 0.7 plus 0.7, and that's going to be equal to about 1.4. That's greater than 1, right? That would be the L1 distance here. It's just the sum of these 0 minus this absolute value is going to be roughly 1.4. So this is greater than 1. So that means that the L1 ball must somehow go underneath here. It's closer to the origin. All right, so people know how this is going to look? I know.
Straight line?
Yeah, straight line. It's going to be a straight line in between these 2 points. Okay, that looks like a weird ball. What's going to happen in the other quadrants? The straight line doesn't continue, right? Yeah, it has to stay down underneath here. So it goes like this. And what you get is this diamond shape here. And it's strictly inside, well, except for these boundary points, inside the L2 ball. So this is the L1 ball. So any point on this line here is going to have this a distance of 1 under this L1 distance. Right? So and you can define this for any other value p. So let's say I took a value of p equal 1.5. What is this going to look like?
It's gonna look weird.
It's going to look weird, but it's going to be kind of understandable, right? It's L1.5 is going to kind of go in between here someplace. It has to lie in between these guys, and I don't know. It's not perfect drawing, All right. Okay, yes, it's not perfect, but it goes someplace in there, right? It's someplace in between the two. This is L 1.5. I use green because it's not. Okay. Okay. What would I could define this for L 0.5, right? So what would L 1/2 look like? Now this one is going to start looking really strange. Like the L 1.5, you know, it's kind of in between here. What could the L 0.5 look like? Is it going to be inside the L1 or outside the L1? What do you think? It's going to be inside of it. Yeah, so it has to, but it has to hit these points still on the corners. So it's going to come, and it's going to kind of come like this inside of here. Kind of like this. So this is L 1/2. You can't really see it perfectly, but you kind of see you can see kind of what's going on here. But the L1 ball is special because it's the smallest value of P where this shape, this ball is going to be convex. Okay, so convex means that if I take any two, say I take any 2 points inside of the ball and I draw a straight line between them, that the straight line stays inside of the ball. This is not necessarily true for the L 1/2 ball, because these 2 points, it's going to go outside. Right? And so this turned out to be a really important property for if you're trying to use this in some sort of optimization procedure. And we'll talk about these a little bit when I give a lecture on compressed sensing. That you can you can solve things with an L1 distance. You can optimize over them. But if you drop p-value below 1, it becomes it's much harder to optimize. You get all these kind of weird local minimum and some optimization function. So L1 turns out to be kind of special in this sense. L2 is special because if I were to rotate the x and the y axes, if I were to kind of rotate how these coordinate system worked, then the distance is going to stay the same, right? So if I were to instead, I'm going to completely butcher this picture. Let me use this highlighter view instead. So let's see what happens. So if I were to make my x-axis look like this and my y-axis to look like this, it's a perfectly valid kind of coordinate system. I could now write every point in terms of this would be x prime and this is y prime. And I could still write every point in this coordinate system. The L2 distance is the same, where the L1 distance is going to be different. It's now going to be pointy along these axes, these new axes. And so if you do this, and we'll actually want to do this for when we talk about doing PCA later, then L1 is going to be trickier the right way to define some equivalent notion of PCA. So people always use the L2 version of this because you're essentially going to be redefining these axes in the process. Right. Okay. So other kind of important versions of these LP distances is the L0 distance. Okay. And so this is kind of so I can write this still in this norm of this vector notation. But this is going to be harder to write as a sum because taking something to the 0th power or taking it to the 1/0 is kind of is not really defined like how we'd want to do it. But so what we do is we look at kind of as these values go towards 0, we'll see what happens, and you end up so typically how people define this is d minus this what's called this indicator function. Actually, it's the sum over these. Hold on. this is I equals 1 to D of this indicator function between AI and BI, and this thing is equal to 1 if A is equal to B and 0, or AI is equal to BI and 0 otherwise. So so basically you're counting the number of elements which are the same. And if all of your elements are bits instead of numbers, then this is the Hamming distance, or is some scaled version of the Hamming distance. Right, so and this L0 you often want to, so when we get back to when we get back to compressed sensing, basically what you want to do is you'll want to find something that matches. You want to kind of have some input B and want to find some A which matches as many parts of B as possible, exactly. And so you want to minimize this D0 distance, but this turns out to be hard, and you end up minimizing the L1 distance instead, because it's convex. And so if I'm trying to draw this, so if I'm trying to draw this L0 distance, it's going to kind of look like these spikes along the axes. And in 2D, it can either, you can only match both if it's at the origin. But it matches, it's kind of 2 points. There's a point here, or it's a point at these points, and it's going to be discontinuous where it's 1. But you can get something, you can look at, so this may be hard. In certain cases, people will look at something like P equals 0.001. You can define a distance this way, and then you can define a ball, and it looks kind of like this L1 half, but it really hugs these lines here, and it's really spiky. It turns out some things you can do for LP distance for any value greater than 0, and so you can kind of force it to look like this. But often cases, the L1 distance will work as well. And then finally, the other one that is useful looking at is the L infinity distance. And this is defined, and it doesn't exactly fit this formula, but it looks like the maximum value I, where the maximum distance between AI and BI. So you look at the maximum difference in coordinates. Okay, so what would the L infinity distance look like in this picture? Is it going to be inside the L2 distance? Or outside the L2? It's going to be outside, right? The bigger the p-value is, the further outside. Can you figure out, what would another point on that ball be? Yeah, so the point 1, 1, or maybe easier to draw up here, let's say minus 1, 1, is going to also have an L infinity distance of 1. And so it's going to look like the square here. So the L infinity, it's still going to go through those axis points, but it's going to be the square. So this is the L infinity distance. And so anything between L2 and L infinity is going to kind of approach this square type distance, but it's going to be curved. And then the L infinity is going to be pointy at the corners. So as long as any one of the values is 1 and the other ones are less, then the distance is 1. So anything along this square is going to have a distance 1 from the origin for the L infinity. Okay, so before we move on, let's mention a couple other things. So remember I said these were shift invariant distances, right? I could write them as this. So I could just look at the difference in the values. Which means that even though I drew this as centered around some point A, which I set equal to the origin, for any point A, in any vector in some d-dimensional space A, a ball around that point is going to look exactly the same. It's just going to be shifted in space. And so if you're looking for all points close to A, say instead of a distance 1, I say I want all the points within a distance 2. Well, they're going to have roughly the same shape, but they're going to be scaled. These balls are going to be scaled further out. Right? So if I have a point A sitting someplace in my space, I want all the close points, they're going to be within one of these shapes. Okay, and what's going to happen, and we'll talk about this more on Wednesday, is you're going to be easily able to find these L infinity balls of points, but you're going to want these L2 balls of points instead. Yeah.
So what's the variable that defines the scale factor?
So you can just put these are just distances. These are balls of radius 1, or the boundary circles of radius 1 under these distances. So if I said radius 2, then it'd look the same, it'd just be twice as far out.
Okay,
right? So
it would just be a phrase that would be given.
Yeah.
So that doesn't show up in the equation.
Yeah, it doesn't show up in the equation. It's just what you set this equal to. So these are all the points. This drawing has gone kind of out of hand, right? But let's write for the L2 distance, this ball is equal to, and say A is in the middle there. So this is all the points B in RD such that the distance 2 of A, B is equal to 1. So it's all the points where it's equal to 1. And if I change this to a 2, it's going to look the same. It's just going to be twice as big. Right? And this can be the same for all the other balls. You can to understand why that's the case, these axis points, this is at distance 1, 0. If I made this 2, 0, all the balls are going to pass through that same point again. Right. Okay, so this is one important thing. The other thing is kind of thinking about in higher dimensions, how would these look? So the L2 ball is still going to be kind of this round ball. Like in 3 dimensions, it's going to be, just like a basketball, right? It's nice and round. The L infinity one is going to look like a cube, right? And the L1 ball is going to look like this diamond, right? So the L1 ball, the L1 ball is kind of interesting in that it'll have kind of a point along each of the axes. And so in between any pair, it's going to have a line, and then kind of this red line here, say in 3D, is going to form a triangle in between the 3 axes, the x, y, and z. And in higher dimensions, this forms what's called in d dimensions, it forms what's called a d-1 simplex. So it's actually going to be a tetrahedron when you're in D4. It's kind of weird to think about. But think of this L1 is going to get really, really pointy. The L2 is going to stay nice and smooth. And so this will have some weird effects. And we'll come back and we'll think about this picture again later in the semester. Okay, but these are all well-defined in higher dimensions, and you can they're higher dimensional analogs of this picture, but it's going to be even messier. So I won't try and draw those. You guys laughed at me enough. Okay, so I kind of want to go back now and talk about locality-sensitive hashing. So remember, we talked about LSH, and we talked about there's some family of hash functions there was this class of things where, let's just define this again briefly. There are going to be gamma, phi, alpha, beta sensitive if the probability, and this probability is over the choice of hash functions for any 2 H and HA, HB, and this is for A not equal to B. that they're going to hash to equal the same value. This is going to be greater than alpha if the distance between A and B is going to be less than gamma, and the probability that they're going to hash to the same thing, you want this to be less than some value beta if the distance is large, is greater than phi. Okay, and if we could define this sort of these sensitivity parameters, then we can use a bunch of these hash functions and use this banding technique to quickly find all the close things. Right, to find all the close pairs, or to build a data structure where we can look up in kind of this set of these banded hash functions to find ones which are likely going to be close. Okay, and so what we briefly talked about was if we looked at the L2 distance, how can we create a how can we create a locality sensitive hash function for some parameters here that worked? And so this will in fact will work for all p values, for all LP distances, for p in the range of 0 to 2. So it cannot work for 0 itself, but any kind of value bigger than 0, this can kind of work. It works less well as you get closer to 0. Okay, so, and basically what we did is we have the hash function works by you have some point A, which was A1, A2, up to AD, some high dimensional point, and you have some, it lies in this space, and we chose this random unit vector, and then we projected onto this random unit vector. So we projected, so we'll call this unit vector U, and then this becomes the point AU. We don't actually need the point. All we need is the distance of this point from the origin. So all we need is this distance. We'll call this AU, and we could say that AU was going to be equal to the dot product of A and this unit vector. Remember, the dot product is simply the sum of AI times UI. So AI is the ith coordinate of A, and UI is the ith coordinate of U. So this is a unit vector. It also lies in this d-dimensional space. Right? So this dot product gave us the length of this projection. Right? So if we can write the norm or the distance of A from the origin. Right? So how does this AU value compare to the distance of A to the origin? Right? So if we look at this distance here, the distance of A to the origin, this would be equal to A minus 0. So let's say under the L2 norm. Right? If we looked at this distance, how does this distance AU compare?
Strictly less than A.
Yeah, so it's always smaller. Well, it could be equal if we happen to get lucky. But it forms a right angle, this projection. It's the closest point. And then, but by the Pythagorean theorem, this distance plus this distance is going to be, well, this distance squared plus this distance squared will be equal to this distance. But by the triangle inequality, from going from 0 to AU, to the location here, plus the distance of the projection should be more than the original distance. Right? So this, when I project down, this distance is going to be shorter than before. Anytime I do a projection, you're kind of losing distance a little bit. But you kind of know that you expect this distance, if you chose this at random, the expected value of AU is going to be the norm of A divided by D. Or if I looked at the squared value here, the squared. That's going to be the case. And this is going to be because you can decompose this L2 distance along here. This property doesn't necessarily hold for all LP distances, but you can drive other bounds in this way, similar. But you can know that it's going to shrink. The squared value of it will shrink by about a factor d. And so you kind of, what you want to do is, if you want to estimate the expected distance of this, you can do so by doing the projection and multiplying by d, and that'll be the right expected value. Right, so if I put this d to this side, d times this is equal as the right expected distance here. Okay, so then to build this hash function, what I did is I divided this up into these bins. There are a couple things that I didn't get finishing explaining. So you can divide these up into these bins, and we're going to call these bins of length, so I match my notes. Let's bin these of length gamma. So the length here is going to be gamma. And so basically I want to kind of think of a locality sense of hash function where my threshold for being close will be basically something that looks like this gamma. So if they're, maybe it's going to be 2 gamma or something like that. And so I'll use this hash function, and if 2 points A falls in this bin and B also falls in this bin, then they're going to be close. Now they could have been on the other side of the boundary. And so basically what I can show is that this hash function is going to be gamma over 2. I used gamma up there, but twice. But so 2 gamma 1/2 1/3 sensitive. Okay, so that means that if the distance is less than gamma over 2, then they're going to collide together at least half the time. That's what this one and this one says. Right? So if you think that's this should be easy to see. If I have 2 things that have less than a distance gamma, what is the only way that they can't collide? So let's say I have another point. I have another point B here. So A and B, and the distance here between them is gamma. Then if they both fall in the same bin, then they're going to collide. If they fall in different bins, they don't. Right? So if the distance is exactly the length of the bin, or is gamma over 2, then at least half the time so if they're like gamma over 2, then the worst case is if A sits right on the boundary, and then half the time B will fall within the same bin. Half the time it will fall outside the bin. If A falls inside the middle of the bin, they'll always collide. Right? But it could be that they fall outside. So that's how you see the first half. The second part is saying that if the distance is greater than 2 gamma, then there's still a chance they collide, but it's less than 1/3 of the time. Right? So how could I have 2 points that are far apart? So let's say this was A, and then point C was out here. So I have A, so this is my point A, and this is my point C. Can these points are further than 2 gamma apart. Can they still collide to the same hash function? Yeah, they're actually they could both project on exactly the same spot. If they happen to be, the distance between the vector between them is orthogonal to my choice of u, they'll project to exactly the same spot. And so then they'll both collide. So this can happen, but if the distance is far, then you can kind of think about like a ball of radius 2 gamma around A, and there's kind of a small area of this spherical cap of the ball, and that happens less than 1/3 of the time. You're going to get the unit vector to be orthogonal to that. And I won't go through the details of there, but there's a bit more explanation in the notes. So you can prove that's this sensitive. Okay. So once you use this, you can combine a bunch of these together, and you can detect distances and high dimensions. And so there's actually there's an open source library out there you can use to do this, and it uses some slight variation of this very, very simple scheme here. And it works fairly well. It's close to state of the art. Wednesday, we'll talk about a couple of other approaches for dealing with Euclidean distance as well. But the locality sensitive hashing can be more general. Okay, so the other thing that I didn't talk about was how do you generate these unit vectors? All right, I briefly mentioned how do I generate this unit vector u at random? So do you want to remember what I said? There's some magical way to do that. So this unit vector u is going to be u1, u2, up to ud. And I can kind of do this. I can do this by, I first set u tilde for each I, and each of these i's are going to be iid from a from a normal distribution. And I think I want to, I forget when I want to set the standard deviation to, but I think it's like 1 over d or 1 over d squared. And you can rescale them afterwards to get it right. So I can do these, and then I can normalize them, so this didn't really matter. But I can draw from a standard, just normal distribution, right? And so this is equal to, actually, write this out. So, or this is equal to 1 over, what is it? Square root 2 pi times this value here is sigma times x of minus. So this is the distribution of some value x. So the over 2 sigma squared. Right. So this is the expected distribution of some single value x according to this distribution. So this is a standard normal or the Gaussian distribution, right? And so if I can draw a random variable from this, and I do that for each of them, and I normalize them, these are it's a very special distribution that gives me a random unit vector. If I did something instead where I wanted a random unit vector. Okay, so I wanted a random unit vector, and let's just look at this in 2D. Right, so the kind of the simple thing people would usually do is they say, well, I know each coordinate is going to be between, say, let's just say in the positive orthant, just to keep it simple, it's going to be between 0 and 1. Right, so this is 0, 0, and this is 1, 1. And so I generate a random x value, and then I generate a random y value uniformly between 0 and 1. What's going to happen is I'm more likely going to get points pointing in the middle than I am going to be pointed along the axes, because there's more length in here than there is along here. Okay, but I want things to lie on this ball, so I want the length inside of here to be the same everywhere. And so if I draw them uniformly independently between 0 and 1, then I'm going to get too much out here. And the Gaussian has this nice property that it's going to be symmetric. So if I want to draw points from a high-dimensional Gaussian, I can draw all the coordinates independently. So, but then how do I draw these points from a Gaussian distribution? How do I draw a value x that satisfies this distribution? So there's this cool transform, or this cool technique. So what you typically can do, and this is in most languages have a, let me just do this on a new page. Most languages have a built-in function where you can draw some value, say u, and it's from uniform in 0, 1, basically ID. So they usually have some function you can call built-in. So we have this utility to draw uniform between 0 and 1, and then there's this cool thing called a box Mueller transform. what it does is it's going to take in two uniform random values between 0 and 1, and it's going to output two Gaussian random variables. Okay, so it's for some reason it needs two, but it also outputs two. And so what you can do is G1 is equal to, and it's kind of funky. It's natural log. It's the square root, the -2 of the natural log of U1 times the cosine of 2 pi U2. And G2 is going to be, this part is the same. Well, that's still U1 here, except I'm going to use a sign here. Okay, so this is kind of a strange thing, but this allows you to get these Gaussian random variables. Okay, and so you can generate these based on these uniform between 0 and 1 random variables. And then you can use these to generate these high-dimensional unit vectors that point each direction equally likely. Yeah.
That's what I was going to ask.
Okay.
So those are the values that give you the distribution inside, or like in the arc.
Yeah, right. So if you generate D of these values here, and then you normalize them, they will lie uniformly on a unit sphere in D dimensions. And so that is your unit vector, and then you project with that unit vector. And so this is known, this Gaussian distribution is what's known as a p-stable distribution. So, and with p equals 2, this is going to be equal to the Gaussian. And so this p-stable distributions have the property that if you generate a random variable from mu p, and you actually generate, I'm going to generate a bunch of these, so x1 up to xd plus 1 of these. Right, so these are all going to be IID out of UP. And this is the Gaussian distribution in the case of p equals 2. Then it has this property, this really cool property that, let's see if I can write this. So that if I have for for any vector v, v1 up to vd, then I'm going to generate two random variables that are going to have the same distribution. So the first one is going to be equal to the dot product between the elements of the vector and these first d random variables. So the dot product here, so this is equal to v dot x, where this is the first d of them. And this will have the same distribution as equals 1 to d times vi to the power p, 1 over p times xd plus 1. Okay, so these are the same distribution, and so this is exactly the p-norm. So this is the p-norm, and so if I take this dot product, and so in this case these were Gaussian random variables, dot product with the vector and divide through by this other one which normalizes it, then it's going to estimate exactly the distance, this distance I want. And so you can replace, for the one norm, you can use what's called a Cauchy random variable instead, and there's a way to generate elements from a Cauchy random variable. And so you can do this LSH with these other LP values, these other LP distances as well, using these p-stable distributions. So this is just kind of a cool trick that, many of you may not need, but I think it's got like a really cool fact. I just wanted to show you guys. So hopefully some of you guys will appreciate that. And okay. All right, so let's get back to some distances that are of interest. Okay, that was kind of a neat aside. Okay, so the next one we'll talk about is the cosine distance. And this will also be a distance in between vectors. So that I'm going to have A equals A1 up to AD, and B equals B1 up to BD. And these are often generated, so these vectors are especially useful, or this distance, when these come from the bag of words model. So this was the thing where we took the documents, and each of the elements here was this first element was like the word apple. It was like how many times the word apple appeared in the document. And so the next word may be like the word aardvark. So that one might be 0, and the word apple might be 2. So it's going to be a very sparse vector. Okay? And so now the cosine distance is going to be defined d cosine of A and B is going to be equal to 1 minus the dot product of A and B divided by the norm of A times the norm of B. Right? And so the, just in case you already forgot what the dot product is, this is just summing up. And so when I say the norm here without a subscript, that's the L2 norm, standard L2 norm. So this, yep. So this distance, so it's very sparse. So that means that I only need to do any computation on the parts that are non-zero, right? So I don't need to do any. I can store these as sparse vectors, and I can just for cycle through the values in say some sorted list. And if there's a 1 in one of them, I check if the next one is a 1 in this one as well, or some other value, and I calculate this dot product. Okay, so so intuitively, what this distance is going to do, and is that you're going to have 2 points A and B. And you're going to think of these now, instead of points, you're going to think of these as vectors, right? Which are going to go out to these points. Okay, that was another failure in my drawing. All right, so let's try this again. Maybe it needs blue. Okay, so think of these as vectors from the origin. And this will measure the cosine of the angle between them. So an angle is something that you think of measuring in a two-dimensional space, but in high dimensions, you can always measure an angle between two vectors because there's only one two-dimensional space that goes through the origin A and B. And in that space, you can measure this angle. And in fact, the dot product is how you measure angles, essentially. So this actually gives you the cosine. So the of this angle between A and B. So this is theta AB is this angle, and this distance tells you the cosine between these. Right? So if these are orthogonal to each other, the distance will be 1, and if they're exactly pointing in the same direction, the distance will be 0. The angle will be 0. Right? Okay, so is this distance a metric? No, I see you shaking your head. Why is this, or were you just yawning out of excitement? What?
It's not a metric.
It's not a metric. Yeah, do you want to say why, or up there?
Oh, I'm just going to shoot in the dark, but is it because we're dealing with distances?
consider dealing with
distances.
with distances. Yeah, I can still measure a distance. The closer these are together, the kind of the smaller the value I'm going to get out of this. So it's a distance, but it's not going to be a metric, which was this thing back here I talked about that had these four properties. Right?
I was going to say that like the 2 points could lie on the same vector line, but still be really, really far apart.
Yeah.
And that violates like the first.
Right. This is going to violate this. This violates, or violated, I guess I wrote, that A and B should be equal to 0 if and only if A is equal to B. But you can have this case where A is here and you set B up here, and so this vector is going to be the same, and then the angle is 0. And so the cosine of the angle is then going to be also 0. Right? So this has removed the scale. This has removed the scale out of these vectors. And that's what's happened here in this part here. I've divided through by the scale. Right? This is saying as A and B get larger, I'm still going to shrink these values back down again. And because if you don't do that, then there's some weird stuff going to the angle, right? So is this necessarily a bad thing? So so what are some advantages of this violation?
Signify like subsets or something that way?
Yeah. So, well, it's not quite a subset. They'd still, if you have two vectors, and you can think of them almost as if you think of them as sets, right? Let's say A was equal to 1, 0, 1, 0, and then B was equal to 1, 0, 0, 0. Then B is essentially a subset of A, but their distance is going to be non-zero. So we've told these apart. What would be an example of two vectors where they would have a distance 0, but they would not be the same?
I think it's that they would have the same proportions of words, but one of them would have a greater quantity.
Yeah, right. So if they have the same proportions, right? So let's say this A was still 1, 0, 1, 0, but if B was 2, 0, 2, 0, right? So think of, if these were representing documents, then maybe B was this document but written twice. You copied the same document over again. So you just put it again twice. So then these would have a distance 0 now under this cosine distance. And so that seems maybe a reasonable thing to do. Or if copies, that's spelled wrong, okay, with multiplicity, these are going to be this, end up saying the same under the distance. What's another example where they might not be exactly the same, but you'd want the distance to be small? But if you didn't have this scaling property, the distance would be large. It's useful, again, to think of this bag of words model for documents, right? How could this be? So let's say you have two documents on the same topic, but one is much longer than the other one. They'll tend to use the same words, but one will just be longer than the other one. And you don't want to say that they're very different just because of the length. Then you're just measuring the size of the documents more than the actual content. So length or size. So it kind of helps normalize out the size of these vectors. You only care about kind of the direction that they're pointing. right? So this is a kind of cosine distances is if you're using this bag of words model, this is kind of one of the main distances that people use. And it turns out there's actually a cool LSH hash function for it. And you define a hash vector, again, say U, for a document A. And this is just, it's -1 if A, U is less than 0, and it's +1 if A, U is greater or equal than 0. And this is for just this is if this is again just a random unit vector. So you can again show that this has these sensitivity properties. So again, this can work at these very large scale settings using this hash function. And that kind of says if it, they're kind of pointing similar. If the dot product is positive, it's negative. If they're both negative, then they're going to have the same thing. If you have some distance pointing over here, then this is going to what separate A and B. But for most unit vectors, they're going to be pointing. You're going to have this roughly the same plus minus values. And it'll map directly to this, allow you to estimate this cosine distance. Okay, so running out of time, I want to mention, let's see here. So that was an example of a non-metric, which is really useful. Another example of something that doesn't satisfy the that doesn't satisfy the symmetry property, or even and it doesn't satisfy the triangle inequality either, although it satisfies some weaker version of it, are these notions of things called divergences. Divergences. So the KL divergence is one example. This stands for the Kullback-Leibler. And so these assume that an input A is kind of representing some sort of distribution. So I'm going to have the property that the sum of the AIs is going to exactly equal to 1, and for all AI is going to be greater or equal than 0. So this is kind of a distribution on these D different entities. So now this allows me to measure a distance between these between probability distributions, and it kind of describes the information between them. And so it's going to look kind of like entropy. And so this will look like let's see. This is a natural log of AI over BI, right? So you can see that this is not symmetric. Distance from A to B is different from the distance from B to A. And it's not going to quite satisfy the triangle inequality either. There's going to be some weird things as these distributions become very skewed in one way or another. But this kind of, if you've looked at stuff with like information theory or entropy, this should look kind of like the definition of entropy. And it's kind of the distance of the information distance between these distributions. And there are other versions of these divergences that have similar properties. And so these are also useful. These are useful in the bag of words model. Again, if you first normalize your vectors, you normalize them so the sum is equal to 1. Then people use distances like these to measure something that these tend to be more statistically robust in some cases than the cosine distance. So there are these techniques for kind of clustering topics on words called like that are under the terms like topic models. And one of the acronyms you can look up are LSI is like the simplest version, and then LDA, latent discriminant analysis, will underneath it, and it's kind of hard to kind of get down to the details, but it uses this distance inside of LDA to kind of understand these classes of documents and kind of find models of topics that these documents are talking about. Okay, in 1 minute left, I want to mention one more distance that's also useful for text, and this is called the edit distance. And so this is, if I were to have two, this is a distance where A and B are going to be words or strings. And so it's like the distance between the word cat and hat. If this was A and B, you can tell I'm a Dr. Seuss fan. And so the edit distance between these is 1. So because I need to edit one of the letters to go from cat to hat. So this is often used if you're doing a spelling correction. So when Google, you type some keyword into Google and say, did you really mean something else? It probably means there's a much more common word that has small edit distance to it that most people search for. And they'll use the edit distance for there. So this is a little bit, you can compute this using dynamic programming. So it's kind of slow. And there's no kind of known good way of doing LSH here. So to compute it, you often need to use some form of dynamic programming. And kind of a key thing to keep in mind is if the edit distance between A and B is, say, even greater than something like 4, or maybe even 3, then these things are probably very far. Then this means very far. You can get between very different words with an edit distance of 4. So often this only works when things are really close to each other. Otherwise, you're going to need to use completely different techniques. Like there are ways of doing like truncation and stuff of words that it works better if your distance is getting larger than 4. But for very small typos, this is often what's used, this notion of edit distance. And this is also a metric. Okay. So that's it for today. We'll try and post the homework probably maybe tonight or probably tomorrow.
What is dynamic programming?
So dynamic programming is kind of a basic thing from algorithms. Have you taken algorithms class?
I'm in there right now.
Okay. So which class? 41?
Yeah, 4150.
I hope you'll learn it in that class. So dynamic programming is when you build up a bunch of. So it's when you're building up some partial solutions and you use those to solve it. So you can think of as